Hey guys, this is notes 13.5. We're going to be talking about equilibrium now. So we've kind of mentioned it, hinted at it and stuff. We're going to get into the details of it in this video. And this is something very, very important. I know I say that with everything, but more and more questions are popping up about this on the Regents. So the first thing, we've talked about this, we've alluded to it in lab and stuff already this year, but let's get a definition down for this. Reversible reaction, guys. All that means is it's a reaction that can occur in both the forward and reverse directions. Okay, so it can go left to right and it can go right to left. All right, so types of equilibrium. First off, let's kind of establish, guys, when we talk about equilibrium, they all occur in closed systems. Closed systems. So if I have a container like this, right, no top to it, so this would be an open system. A closed system just has a top to it, okay? You may see questions dealing with the Regents where it talks about closed versus open containers. Just remember that. It's about equal rates. That's the big idea here, guys, with equilibrium. Equal rates, not necessarily equal concentrations, okay? It's all about the equal rates. So the first type of equilibrium we're going to talk about is physical equilibrium. So these involve physical changes, okay? So phase equilibrium, guys, occurs during a phase change. This shouldn't be anything groundbreaking to us. We've done phase changes throughout the year. You guys did a whole lab where you melted snow and then it heated up and it boiled and all that type of stuff. So anytime you have a phase change, you have phase equilibrium, where let's say if it's solid to liquid, the rate of melting equals the rate of solidification or freezing. Okay? Have you ever thought about it like that? Right? When something's melting, it's also freezing at the same rate. If it's at equilibrium, so it's in a sealed container at 0 degrees Celsius. So when you guys did the lab and we melted ice, it wasn't equilibrium because it wasn't a sealed container. Energy was always getting in. Okay? But if it's sealed at 0 degrees Celsius, your rate of melting and freezing are equal. So it looks like nothing's actually happening to your substance because the rates are happening at the same time. Same likewise with liquid to gas, right? The rate of vaporization or boiling equals the rate of condensation. Again, sealed container at 100 degrees Celsius. So remember, phase equilibrium occurs during any phase change. Don't make it harder than it needs to be. Phase with phase. Now, the other type of physical equilibrium is solution equilibrium, which occurs in solutions. Go figure, right? This is what's called or at the saturation point. So we've talked about saturated solutions and unsaturated. Something we're going to come back and review a whole lot more of when we do our Regents prep for sure. All right, saturation point, this is where you have the rate of dissolving. Okay, so you know, things you put in are breaking down into smaller particles or becoming ions. So the rate of dissolving equals the rate of crystallization. Okay, so not only are things dissolving, but then they're re-solidifying, becoming crystals again. An example of this would be NaCl solid and NaCl aqueous. Okay, so it's dissolving and crystallizing at the same rate. Okay, so that's it for physical equilibrium. Just say phase changes and saturation point. That's the key you want to remember with those. Now, chemical equilibrium is now talking about those kinetics, going with what we've already talked about, reaction rates and things throughout the whole unit like we've been dealing with. That's chemical equilibrium. So this is talking about the rate of reaction. Okay, so reaction rates is what we're talking about here, i.e. kinetics. What are the particles doing? And I've got two really good graphs here. These are great pictures to kind of show you that. Maybe make a flashcard or two with them. Draw these graphs. You know, it can just be sketched very, it doesn't have to be great. It can be just, very quick. But they're great to know. And I guarantee you will see a question or two like this come June. So make sure you know what's going on here. So this first graph is dealing with rates of reaction. So the reverse rate versus the forward rate. So if we're in equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. Okay, so notice, it comes to an equilibrium because you're forward. Okay, so all your reactants, they're reacting together, reacting together, reacting together. Eventually, they're going to be used up and they kind of steady off. Well, the reverse reaction now is, okay, my products are reacting to reproduce the reactants, and they're going to get to an equal rate eventually. Again, in a closed system. If it's not a closed system, it may not be that case. And we'll talk more about that in the next video when we talk about equilibrium shifts. But the rate of the forward equals the rate of the reverse. Eventually, they will, over time, become equal rates, so it doesn't look like anything's happening in the reaction. It's just stationary. It's steady. Now remember, not all reactions are reversible, but we're talking specifically about reversible reactions here. So a lot of acid-base reactions this would be, where you can kind of go between pHs and stuff like that. Those are great examples of equilibrium. Now, so this first one, guys, is dealing with rates, okay? This one's dealing with concentration of your pieces, okay? Concentration of your reactants and products. So it's still going to be, we're going to say rate because that's, you know, the best way we can look at it, but this would be the rate of breaking bonds and the rate of forming bonds are equal, okay? Now, this is different. When we talk about rates of reaction, like the speed, okay, how fast the forward reaction is happening versus how fast the reverse reaction is happening, so speed, we could say, okay, eventually those rates, those how fast they're forming, they will even out. Here, though, when we talk about concentration, it's not necessarily that they're going to even out and be the same amount. Okay, so notice how the amounts can be different. What you're looking for here is that they just taper off and become flat, so they flatline. Okay, so equilibrium is no change in amounts. So your reactants will maybe be lower than your products, but it doesn't matter. They all flatline and they stay steady. So this is something very important here, guys, with this. Constant is the key. Okay, constant amount is what you're looking for when it talks about the rate of breaking bonds and forming bonds. So there's two things. So the speed at which the reaction happens or the amounts, okay? So constant amount, not necessarily the same amount. Okay, so that's something you got to know, and I know a lot of people are going to miss this. So constant amount, not necessarily equal, okay, in terms of the concentration. So notice how both have flat lines, so their amounts are staying constant, but they're obviously not the same amount because one is lower than the other. All right, so this is why flashcards would be a great tool for you guys to use. So an everyday example of equilibrium, right? Students changing room. All throughout the day, you have different rates of students coming and going. Eventually, you know, during the periods, they should pretty much stay constant. But then in between class changes, that's where the rates will pick up, and they won't stay constant per se. Okay? So, chemical, guys, you've got to make sure that you understand this and know this, and it's conceptual. It's all up here. You've got to know the concepts behind it, so terminology and things like that. So you've got two different types of chemical equilibrium. The rate, where they eventually even out, so rates do become the same, or you have it in terms of like concentration or amount of reactants and products, where they just stay constant. All right? So, last thing we're going to talk about here with equilibrium is the equilibrium constant. Now, you guys will not have to do any math in this class with it, but I want you guys to be aware and know how to write what's called a K expression. Okay, K just means equilibrium constant. Okay, it could be KEQ or KC. If you see anything, guys, it would probably just be K or KEQ. So don't stress about it. And it's products over reactants. That's the key you want to remember here, guys, is products over reactants. Any coefficients that products or reactants have in terms of concentration, like so moles, they become superscripts. So what K allows us to do is, if K equals 1, it's equilibrium. If K is less than 1, the reverse reaction's favored, means you have more reactants. And if you take a look at this graph, right, if I have 1 over 5, that's less than 1. okay? And if it's greater than 1, the forward reaction is favored, means more product, so 5 over 1. Now, again, what I want to make sure you guys know, you won't do any math with this in this class. Those of you thinking about AP, yeah, we'll get into this in much more detail when you get to AP. But for you guys, all I want you guys to know is how to write a K expression, just in case you see it on the Regents. And they're actually very simple. It might be confusing at first, but I promise you it's going to be super easy. Now, one thing to note is that K only includes gases and aqueous solutions because they're the only ones that have a concentration. Solids and liquids do not have concentration. All right, so keep that in mind. We're going to write a K expression for this reaction. So first thing, cancel out any liquids and solids you have. All right, we have all gases, so we're going to use every piece here. So K equals, if I look up here, guys, products over reactants. Remember, what do those brackets mean? Brackets just mean concentration. So let's identify my products and reactants. So I'm going to take care of all my products first. They're going to go on the top of my fraction, and then I'm going to worry about my reactants on the bottom. So how many products do I have? I've got 1. So I'm just going to put it in brackets. So I've got NO. Do I have any coefficients for NO? Absolutely. So because this is a coefficient, it becomes a superscript. That's it. That's all I have to do. Now I'm going to do the same thing with the bottom. Now, how many reactants do I have? Notice how I have 2. Guys, notice a plus sign means that, hey, they're not one substance together, right? They're 2 separate substances. So we got to treat them as 2 separate substances, meaning they each have their own concentration. So I'm going to have 1 bracket for N2, and I'm going to have 1 bracket for O2. They're not added together. They're not in the same brackets. They're separate. Do either of those have coefficients? No, they don't, so their coefficient would be a 1, which we don't need to write. That's my K expression, guys, right there. That's all I have to do. So I want you guys to try this on your own. If you feel good, pause it. Otherwise, I'm going to kind of go through and write these as well. So A, products over reactants. So K equals, how many products? I've got 1 product, so it's CO2 in parentheses. It's got a coefficient of 2, so I need a superscript of 2. On the bottom, oh, notice I've got 2 reactants, so they're each going to get their own bracket. Do either of them have any superscripts? Well, CO2 has a 2. I'm sorry, CO has a 2, so I need to put that up there. O2 doesn't have anything, so I'm just going to leave it as is. So now, again, if you saw another one, you feel good, great. If not, and try it on your own, good. If not, I'm going to keep working. B, cross out solids, right? Solids play no part. So my K expression here is, well, the only thing I have left is CO2. Is that a product or a reactant? It's a product, so it's just going to be CO2. All right. I'm going to go a little bit quicker here with the rest. All right. C, I have 1 product. That's SO3, and it's going to be squared. Then I have SO2 on the bottom, and that's squared. And I have O2. There's my K expression for C. D. All right, everything is going to be included here as well. So K equals HCl, and that's squared because it had a coefficient of 2. And then on the bottom I have H2 and O2, and that's it. And lastly, E, K equals my product, which is NH3, and it's squared. And then I've got N2 on the bottom, and I've got H2, and H2 is going to be cubed. All right? Till next time, I'll see you guys later.